Recently I was asked about muscle systems in KineFX. KineFX does not yet have any muscle system related to it. However, because KineFX is part of SOPs, it is easier to create a custom muscle system for it. Personally, I don't use muscle systems very often. The main focus of my use of Houdini is on games. Another reason is that my personal rig is just not powerful enough to use muscle systems. Muscle systems can be very expensive. The final reason is muscle systems are hard to get right. While they can provide excellent results, it takes a lot of time to set up a proper rig with a muscle system, and none of the work which I'm currently doing requires that amount of investiture on a single character. That kind of investment is more likely to be used for film or advertising. With that said, this is a basic approach you could use to create something like a muscle system. Unfortunately, as I've said previously, my system is not powerful enough to test or run a system like this properly, so this is purely as a proof of concept. The scene contains a skeleton, and I've created a very basic skeleton for my character. Basically, the spine, head, neck, arm and leg. What I'm basically going to create is a bicep and a tricep. I will start by getting an add node. I'll call this node bicep. Now we only really need 2 points, but I will use 3 points for the bicep, as this will allow me more control over the shape of the muscle. I will then select the polygon tab and the by group tab in order to turn this into a line. I can now position the points. The first point will be the shoulder attachment, and the last point will be the forearm attachment. I'll then create another add node. I'll call this node tricep. For the tricep, I'll just use 2 points. I'll position the first point near the top of the upper arm, and the second point will be positioned near the elbow. I'll then get a group node. I'll set the group's name to $OS, and I'll rename the node to bicep group. I will then duplicate the node, and I'll call the duplicate tricep group. The group type for both of these nodes should be points. I now have my muscle groups, and I'll want to convert these into joints. In this case, I'll use the rig doctor node to make the conversion. I'll set the prefix to be bicep. I'll then initialize the transforms. I'll want these joints to have the same transform space as the joints of the skeleton. If you take a look at the joints of the skeleton, I'll do this using the visualize rig node. We can see that by default the skeleton node will orient the joints with Z as -1. I'll use this as well with my rig doctor. We'll select reorient child, and I'll set the Z to be -1. I will repeat this for the tricep. I will then get a merge node, and I'll connect the joints to it. I'll then get another merge node, and we can connect the muscles to the skeleton. I'll then add a color node, and I'll color my muscles red to make them more visible. We'll now attach the muscles to our arm. I'll be using a reparent joint node for this. We'll start by attaching the bicep to the arm. So joint 1 will be bicep 0, and the parent will be the arm. I'll also make the middle point of the bicep, bicep 1, the child of the arm. Bicep 2, the final bicep joint, will be connected to the elbow. I'll then connect the tricep. Tricep 0 will be attached to the arm, and tricep 1 will be attached to the elbow. Now the points are parented to the arm, but they're still parented to each other. So I'll add a reparent joint. This will be added after merging the muscles. I'll set this to reparent all of the joints with star, and I'll leave the parent empty to unparent all of them. Now all of the points for the muscles are attached to the arms. Add a rig pose node, and now I can test that the points are following the arm bones correctly. The muscle itself can now be added. I'll start by getting a blast node, and I'll select the bicep group, and we'll delete everything that is not part of it. I'll now be making a curve from my points. I'll get an add node, plug it into the blast node, select the polygons tab, and select the by group tab. Next we'll add detail to this curve, and we'll do this with a sample node. We do not want the length of the muscle to change, so turn off maximum segment length. Instead we'll use maximum segments. You can also get a smoother curve by setting the curve interpolation. This can be set to either subdivision curves or interpolating curves. I can then add a sweep node. I'll then change the surface shape to round tube. This will give me my muscle. I can then give my muscle shape using apply scale along curve. I will then use the curve to adjust the shape. I will also convert the points to Bezier points. And now I have a working muscle. For a more efficient muscle system, I wouldn't take it much further than this, but for this example I will take it further just to show what can be done. Needless to say, this is not particularly well set up. I've not spent a lot of time on placing the muscle correctly, and placement is very important for muscle systems. Now we can examine using the length of the curve to drive the width of the muscle. This will allow us to customize the expansion and the contraction of the muscles. I will select the resample node, and I'll look at the primitive numbers. In this case, we only have one primitive. This is useful as it allows us to select the entire curve as a primitive. I will add an attribute create node after the resample node. We'll add a detail attribute as we only need this attribute once for this curve. It will be a float, and I'll name this attribute length. I'll then set this attribute using the arc length function. The surface input will be 0. The primitive number will be 0. The start of the curve will be at 0, and the end of the curve will be at 1. And this will give us the length of the curve. I can then use the length attribute to drive the radius on the sweep node. To access it, we'll use detail. The source will come from the input, so this can be set to 0. The attribute name is length, and detail attributes will always have the index 0. So this will allow us to use the length to drive the radius of the muscle. The problem with this approach is that we do not have much control over the length, so I will not use this method, and I do not need the attribute create node, so I can remove it, and I can remove the references to it from the radius. Instead of working with the muscles directly, I'll calculate a length based off the rig pose, and this length will use the distance from the shoulder to the wrist. I'll add a blast node, and I'll connect it to the rig pose node. I'll then select the points I want, the arm, the elbow, and the wrist. I'll then delete the non-selected points. For the sake of brevity, I'm going to get the length of these lines using a convert line node. This node will convert the edges into individual primitives. It will also give us a rest length for the edges. I will, however, rename the rest length attribute to arm length. I'll then get another blast node and I'll delete the middle point from the arm. This will give me the distance from the wrist to the shoulder. I can also do this using the delete joints node. The blast node is not the most efficient node to use. I'll calculate the length of this using the convert line node as well. I will rename the rest length attribute to dist. If you're using this in an actual rig, it would be best to calculate this using a wrangle node, as the calculation is not particularly difficult. It will also be much faster than using multiple blast and delete nodes. We can now use these distances in a wrangle node. In the wrangle node, I'll start by creating a length attribute. This will need to be a detail attribute. I will now calculate the length of our arm, and we'll do this using a for loop. For I is equal to 0, I is less than the number of points. This will give us the number of points being passed through the first input, and then we'll increment with I++. We'll do this adding the arm length for each of the bones in the arm. We'll add the arm length to the length value, attribute length, plus equals, this is a primitive attribute. It will come from input 0. The attribute will be arm length, and the primitive number will be I. I'll then create another attribute which I'll call weight. This attribute will contain a normalized version of the distance from the shoulder to the wrist. I'll get this using the fit method. We'll be fitting our distance attribute. This will be done using the prim command. This will be using input 1. The attribute will be dist, and we'll get this from the first primitive, which is primitive 0. The original value will vary between the range of 0 and the length of the arm, and we'll convert this to a range between 0 and 1. The attribute name should be a string, and I now have a value for the distance my arm has moved, which is based between 0 and 1, which makes it far easier to use this distance to drive a parameter. I will then rename my attribute wrangle node to weight. I can now use the weight attribute to drive the radius of the muscle. I'll go to the radius parameter, and this will be a detail attribute. The first parameter is the node which I need to get the detail from, and we'll use a string to reference the weight node. The attribute's name will be weight, and as it is a detail attribute, the index will be 0. As you can see, the result is way too large. We also have the problem that the behavior is the opposite of what we want. The muscle is expanding when it should contract, and contracting when it should expand. I could handle this with an expression, but for clarity we'll get an attribute wrangle node. This node will go between the resample and the sweep. I'll plug the weight node into the second input, and this will be a detail attribute. I will then remove the expression from the radius parameter. I can then edit the parameter interface. I'll add a new folder. I'll add a float, and I'll duplicate this float twice. Then I'll add a toggle. I'll call the toggle reverse. I'll call the first float scale. I will then have a min value and a max value. I'll then apply that to add the parameters to my wrangle node. I'll now start working my vex code. I'll add a float variable for the weight, and this will be called weight. I'll set this variable from the first input. Detail, we'll use input 1. The attribute is weight, and the index is 0. I'll then create an extra attribute for the muscle weight, and this will be called mWeight, and for now I'll set this to be equal to weight. But we'll be setting this based off the reverse parameter, so we'll need a conditional for that. If the channel is a string channel, so we'll use CHS. Usually one would think that Boolean channels would be integers, but Houdini treats them as strings with values of on and off. Channel name is reverse, so we'll check if reverse is equal to off, and off will be a string. If it is off, mWeight will be 1 minus weight. Else, mWeight will equal weight. And as I said earlier, off should be a string. I can then apply this, and we can see that if I use reverse, I'll change the value of the weight. I can now set the radius and sweep node to equal mWeight. This will be done using a detail attribute. Detail, the input will be 0, the attribute will be mWeight, and the index will be 0. The arm is now driving the muscle correctly, but I can still get the other behavior if I choose to reverse this. And I'll need this behavior for my triceps. I can then multiply the muscle weight by the scale. Attribute mWeight times equal, we'll get the channel width, CHF, and the parameter name is scale. This will give me a global control over the weight of the muscle. However, we now have the problem that the muscle is going to be either too big or too small. So we're now going to set a range for the muscle. We'll do this using the clamp function. mWeight will be assigned clamp, and we will be clamping mWeight, and the minimum will be using CHF, and the channel we're referencing is min. The maximum will use CHF, and the channel we're referencing is max. And I can now set the bounds for the muscle. This will allow me to have a more expressive expansion and contraction on my muscle. For the tricep, I'll use the same setup. I'll duplicate the setup for the bicep. For the blast node, I'll set it to use the tricep group instead of the bicep group. I can then tweak the shape of the muscle, and I can reverse the expansion and contraction for the muscle, as this will be the opposite of the bicep. Next, I'll need to attach the character to the rig. I'll start by capturing weights for the character. I'll need an object merge for the mesh, a bone capture lines node, a bone capture biharmonic node, a tet embed node. I'll connect my skeleton to the bone capture lines. The bone capture lines node should be connected to the tet embed node. The tet embed node will be connected to the bone capture biharmonic node. The object merger will be connected to the bone capture biharmonic and the tet embed nodes. In the tet embed node, enlarge input mesh should be turned off. I'll turn off capture pose in the bone capture lines node, and then I'll reference my geometry in the object merge node. I'll then get a stash node so that I can cache this. I will then deform my mesh with the bone deform node. The first input will be connected to my stash node, and the final input will be connected to my pose node. Now I have basic skinning for my mesh. I'll then merge my bicep and my triceps. I can then use the muscle deform node to add the muscle deformation, and I can start to work on the muscle deform settings. As I stated at the beginning of this video, my system is not really powerful enough to handle a proper muscle system. This system is also not particularly well optimized. The section of the system which adds the radius control for the muscles is probably overkill, and you can probably get away without using it. This section should also be converted to just using a single wrangle, and most of these processes could be handled purely in Vex, which would be a lot faster than it currently is now. This would also remove the blast nodes, which would speed up the system considerably. As I said at the start of the video, muscle systems are not really appropriate to what I'm currently using Houdini for, so I will not be exploring this any further, but hopefully if you're interested in muscle systems, this could give you some idea as to where to start with muscle systems with KineFX.